Alright guys, from this video we get into chapter 5 and we start with 5.1 jointly distributed random variables. First of all, let's take a look at the two discrete random variables here. So definition, let x and y be two discrete random variables defined on the simple space S of an experiment. The joint probability mass function P of xy is defined for each pair of numbers x and y by P of xy is equal to the probability that x is equal to the little x and y is equal to the little y, and we get an n in the middle. So it must be the case that the P of xy is greater than or equal to 0, and the sum of the joint probability mass function over both x and y is equal to 1. So actually, the idea here is very similar to the idea we saw in the previous two chapters, chapter 3 and chapter 4. So for being a qualified PMF or PDF, we know that the value of the PMF or PDF got to be greater than or equal to 0, and the sum of the all PMFs is gonna be equal to 1, and just like that, just like the sum of a PMFs is equal to 1, and the integration from negative infinity to positive infinity, the PDF is equal to 1. Of course, we have a dx over here. So basically, which means that the sum of all probabilities is equal to 1. So same thing here. The P of xy is greater than or equal to 0 means each probability got to be greater than or equal to 0. And the sum of all PMF, joint PMF over both x and y here is equal to 1, which means the sum of all probabilities is equal to 1. Okay, so actually the idea here is very similar to the idea we saw before. The only difference is that we are dealing with two random variables. Okay, of course there are going to be two different cases. One is what we're talking about now, about two discrete random variables, and of course in the future, I mean later on in this video, we're gonna see the case there are two continuous random variables. And now let A be any set consisting of pairs x and y values. For example, A is equal to x at the pair x and y, such as x plus y is equal to 5, or the max value of x and y is less than or equal to 3. Then probability that the outer pair x and y in set A is obtained by summing the joint PMF over pairs in A. So actually, this is a very important. It's very similar to what we saw before, which is for example, if we want to see that we have discrete random variable, and if we want to find the probability, let's say x is greater than or equal to A, less than or equal to B, then that would be equal to sum of x belongs to A to B, and then P of x, right? I mean, I think it might be a good idea to use that. Use let's say x in the set A and x in set A. Okay, that's for discrete random variables. If it's continuous random variable, so let's say if we want to find the probability that x is greater than or equal to A, less than B, so that would be equal to the integration from A to B f of x dx. Okay, that's what we learned from chapter 3 and chapter 4. And a very similar idea here, the probability outer pair x and y in the set A is going to be equal to the sum of the joint PMF over x, y, and A. Okay, I think this is quite straightforward, and I hope this is clear enough to you. And if it's not, let's take a look at this example here. I think the example will make everything clear. So given the joint probability distribution below, since it's the joint probability distribution, which means we're dealing with two random variables in this case, of course, we have x and y, and we have the probabilities of each other pair. And then the p of 100 and 100. So based on the definition we have here, the probability of x and y is equal to the probability of the random variable is equal to the little x, and the big Y is equal to the little y here. So same thing over here. If we want to find the probability of x and x, which means we're looking for the probability x is equal to 100 and y is equal to 100. And then we just need to locate to find the probability in the joint probability distribution and see which one is for both x and y are equal to 100. Now we can tell the first row here is for x is equal to 100, and the second column here is for y is equal to 100. So of course this number at the intersection point is the probability for both x and y is equal to 100, which is 0.1. That's where the 0.1 coming from, okay? And this because this is the probability of this outer pair in the joint probability distribution for x and y are equal to 100. And then let's take a look at what is the probability x is greater than equal to y is greater than equal to 100. So since we're looking for the probability that y is greater than equal to 100, we don't have to worry about x. X could be any value it could be. Okay, we just need to guarantee y is greater than equal to 100. Now let's take a look at the joint probability distribution here. We can tell the possible values for y are 0, 100, 0, 100, and 200, right? And the possible values for x are 100 and 250. Now we want to guarantee y is greater than equal to 100, which means y could be either 100 or 200, because only those two values will guarantee this inequality y is greater than equal to 100, and we don't have to the value of x. So which means when y is equal to 100, x could be 100. When y is equal to 100, y could be 50 as well. When y is 200, x could be 100, and when y is 200, x could be 250 as well. So in other words, if we are looking for the probability y is greater than equal to 100, we are looking for this outer pair 100, which is 0.1, and 250, 100. The probability of this outer pair is 0.15, and then 200, 100. 100, 200. And the probability of this outer pair is 0.2, and then x is 250, y is 200, and the probability of this outer pair is 0.3. Okay, so if you add those four probabilities together, so you will have, of course, this is equal to 0.1 plus 0.2 plus 0.15 plus 0.3, and you will have this whole thing is equal to 0.75, and this is where the 0.75 coming from. So once again, if you are looking for the probability y is greater than equal to a number, you don't have to worry about the exact value of x. X could be any number it could be. Okay, we just need to guarantee y is greater than equal to 100 in this case. All right, I think this is I hope this is clear to you. All right, once it is, let's take a look at what it's talking about here. Once the joint PMF of the two variables x and y is available, it is in principle straightforward to obtain the distribution of just one of those variables. As an example, let x and y be the number of statistics and the mathematics courses respectively currently being taken by a randomly selected statistic major. Suppose that we wish the distribution of x, and that when x is equal to 2, the only possible value of y are 0, 1, and 2. And then the p sub x of 2, of course, this is equal to the probability of x is equal to 2. So as what I just mentioned up here, if we are looking for the probability that x is equal to 2, we don't have to worry about the value of y. Y could be any number it could be, okay? We just need to guarantee x is equal to 2. So of course, when x is equal to 2, y could be 0. So we need the probability 2, 0. Of course, when x is equal to 2, y could be 1 as well. So we need the probability 2, 1. And then when x is equal to 2, y could be 2 as well. So we need the probability 2, 2. If we add those three probabilities, together, we will have the probability x is equal to 2. Okay, and that is the joint PMF is summed over all pairs of the form 2y. Okay, y represents all the possible values of y here, because if we are looking for the probability of x is equal to 2, we don't have to worry about the exact value of y. It could be any number, it could be, okay? More generally, for any possible value of x, the probability p sub x, x results from holding x fixed and summing the joint PMF p of xy over y, for which the pair xy has positive probability mass. The same strategy applies to obtaining the distribution of y by itself. What does it mean? That means if we want to find, let me take a look at, yes, actually we do have the definition here. Let's just take a look at the definition of marginal probability mass function directly. So the marginal probability mass function, denoted by p sub x of x, is given by p sub x of x is equal to the sum of all joint PMF over y, okay, for each possible value x. Similarly, the marginal probability mass function of y is equal to the sum of the joint PMF over x. So which means if you want to find the marginal PMF of x, you need to sum up the joint PMF over y. Okay? Because in this case, x is a random variable. Okay? The sum the joint PMF over y to find the marginal probability mass function of x. Similarly, if you want to find the marginal PMF of y, you need to sum the joint PMF over x, because in this case, y is a random variable. All right. So once this is clear, let's just take a look at this example here, 5.2. Actually, this is a continuation of example 5.1. Let's just go back to the joint probability distribution here. Now, let's take a based on the joint probability distribution here. Let's take a look at how can we find. Let me clean this for quick. How can we find p sub xx and a p sub y of y? So if we want to find the marginal PMF of x, so based on what we learned in chapter 3, we know if we want to find a PMF, first of all, we want to list all the possible values of x and then find the probability of each possible value. Okay, so in this case, x could be 100 and x could be 250. We have already got the possible values of x, and then we just need to find the probability of each. Now let's take a look at how to find the probability x is equal to 100. So once again, if we want to find the probability x is equal to 100, we don't need to worry about y. So we just y could be any number it could be. All right. So in other words, which means the probability x is equal to 100 would be equal to this plus this and plus that, which means this is equal to the p of 100, 0, y 0 plus the p of x is 100. Of course, y could be 100 as well. And then plus the probability of x is 100, y could be 200. Right? So x, we just need to guarantee x is 100. Let me clean this for quick and rewrite it later. So x, we just need to guarantee x is 100 and y could be any number it could be. And then this is equal to 0.2 plus 0.1 plus 0.2, which is 0.5. All right, similarly, x is equal to 250. So that would be equal to, of course, we just need to guarantee x is 250. Y could be any number it could be. Of course, y could be 0, y could be 100, y could be 200. So in other words, the probability x is equal to 250 would be equal to the p of 250, that's for x, of course, y could be 0, and then plus the probability of 250, and y could be 100, of course, and then plus p of 250 and 200. Y could be a 200. If you add those together, 0.05 plus 0.15 plus 0.3, that would be equal to 0.5. Okay, now we have already got the probability of each possible value of x. Now we can just write up the marginal PMF of x. So let me clean this for a quick. Oops. Let's just get back here. Let me write down the marginal PMF of x. P sub x of x. Of course, it should be the little p. P sub x. That would be equal to. Since the probability is 0.05 for both. X is equal to 100 and 250, so we can just write them together. So the probability mass function, or the probability, is equal to 0.5. X is equal to 100 and 250, which means when x is 100, probability is 0.5. X is 250, the probability is 0.5 as well. And then don't forget 0 otherwise. Don't forget that. This is very important, okay? All right, similarly, let's take a look at how to find, let me clean this for a quick. Let's take a look at how to find the marginal PMF of y. So as what I just did, we need to find all the possible values of y. So of course, in this case, y could be 0, 100, and 200, right? And then we just need to find the probability of each. So first of all, let's take a look at probability y is equal to 0. So once again, if you want to find the probability of y is equal to 0, you don't have to vary about the exact value of x. X could be 100, x could be 250. So the probability of y is equal to 100 would be equal to the p of 100, 0, plus p of 250, 0. Okay? X could be 100, x could be 250. We just need to guarantee y is 0. So this would be equal to 0.2 plus 0.05, which is 0.25. And then let's take a look at the probability y is equal to 100. So of course, when y is equal to 100, x could be 100, or x could be 250 as well. So that would be equal to the p of 100. That's for both x and y are 100, plus the probability 250, 100. So that's for x is 100, x is 250, but y is 100. So this would be equal to 0.1 plus 0.15, so which is 0.25. And then we need to find the probability y is equal to 200. Of course, if y is 200, y could be 100 or 250, so that would be equal to p of 100, 200, plus the p of 250, 200. That would be equal to 0.2 plus 0.3 is 0.5. Okay, let me clean this for a quick. Of course, 0.2 is coming from here, 0.5 is coming from here. Now we get the probability of each possible values of y. We can just write down the marginal PMF of y, okay? P sub y of y is equal to, now we can tell that the probability of y is equal to 0 and 100 is 0.25. So we can just put them together. 0.25 for y is equal to 0 and 100. And then the probability is going to be 0.5 for y is equal to 200. And of course, 0 otherwise. Don't forget that. All right, that's pretty much how we find the marginal PMF based on the given joint probability distribution. Okay. All right. So once this is clear, let's just read over the solutions given here. This is pretty much the exactly same thing as what we just did. So of course, if you want to find the marginal PMF of x, you want to find the probability x is equal to 100 and probability x is equal to 250. So of course, when x is 100, y could be 0, 100, or 200. If you add them all up, we get a 0.5. And of course, when x is 250, x could be 0, 100, or 200. If you add them all up, you get a 0.5 as well. So since we got the same probability, we can just add, put them together. The marginal PM of x is P sub x of x is equal to 0.5 when x is equal to 100 to 50 and 0 otherwise. All right, similarly, for the y, we got the same thing as what we got above. About here. About here. So when y is equal to 0 or 100, the probability is 0.25. When y is equal to 200, the probability is 0.5 and 0 otherwise. Okay. So actually, we can find the probability of this interval with if we find the marginal PMF of y already, we can actually find this probability by adding those two together. Okay, because this is just we already have the PM of y. If we want to find the probability of y is greater than or equal to 100, we just need to add the probability y is equal to 100 plus the probability of y is equal to 200 together, okay? Which is equal to the probability when y is equal to 100 is 0.25, and the probability when y is equal to 200 is 0.50. So if you add those together, you get a 0.75. All right, that's pretty much all about the joint PMF of two discrete random variables, and I wish that is clear to you.